This video is going to be a discussion about measures of spread. We're going to learn about 3 measures of spread. The first being standard deviation, which again, I'm going to put a star by that one. That's going to be the big one we focus on for the majority of our course, and that's where we're going to focus on in this video. And then we are going to look at range as well as what are called quartiles. So those are the 3 ways we're going to measure spread. We're going to start here, like I said, with standard deviation. And so standard deviation is going to be a measurement of how far, on average, each of our observed values in our data set lies from the mean, the center of that data set. So we're told here that standard deviation is not going to be resistant, meaning that if there are potential outliers, the standard deviation will get inflated, it will get larger. And that's because we're basing the standard deviation off of the mean. And remember, the mean was not resistant either. We're going to talk about some notation here, which is if we're finding the standard deviation for a sample, we're going to use lowercase s. This is really important as we move through the course so that we understand the notation. If we're looking at a population standard deviation, so we're calculating a standard deviation for a whole population rather than a sample, then the notation changes to lowercase sigma. It looks kind of like an O with a curly Q on the top. Okay, so if it's population, it's sigma. If it's sample, it's S for standard deviation. All right, so a few facts about standard deviation, and then we'll look at calculations. First thing is a standard deviation is always 0 or positive. Remember, by definition, this was a measurement of how far, on average, an observation is from the mean. It's a distance, right? How far is a distance? It cannot be negative. It's going to be 0 or positive. A small standard deviation is going to indicate that your data values are closely clustered around the mean. And then a large standard deviation would mean that the data values are more spread out from the mean. So we're going to look at an example here, calculating actually 2 separate standard deviations. We're going to do it once by hand, and then I want to show you on the calculator as well, each for a different data set, so we can kind of get an idea of how to compare these. So we're told that the GPA for a sample of 10 non-honors college students and then 10 honors college students were obtained for a study, and then we're given those GPAs below. So I think what we would expect to see is what we're seeing here, which is that in the non-honors college, we have some fairly low GPAs, right? Like 1.55, really low. We also have some fairly high GPAs, 3.80 so really is a nice high GPA. And so there are a variety, right? A lot more spread, a lot more variability in the GPAs for students that are not in the honors college, because they could be performing low in terms of GPA, or they could still be performing high and just choose not to be in the honors college. Versus those that are in the honors college, by definition, one of the requirements is that you have a high GPA, and so you'll notice there is very little spread, very little variability in the range of values for the honors college, right? The smallest it looks like is 3.84, and then the largest 4.0, so very little spread there. All right, so what we're gonna do is we're going to use the formula, which looks like this, for calculating sample standard deviation, and we're going to do it with the non-honors students, so that's the top row of data here. So I usually do this in a table if I'm doing it by hand. I think that's the easiest way to stay organized. So first column I have labeled as X. That just means what are the original data values. So we've got 3.80, 3.85, 3.80, 1.55, 2.24, 2.89, 3.0, 2.76, 3.26, 2.14, 2.0, and 2.71, and if you'll notice, I left us an extra line down here at the bottom. Okay. The next thing that we would need to do is we would need to take the observed x values here and subtract the sample mean for each of those data values. So we have to find the sample mean first, okay, which would be adding all these up. All right, we just learned how to do this in the last section, and divide by 10. Okay, so if we do that real quickly, we've got 3.8, 1.55, 2.24, 2.89, 3, 2.76, 3.26, 2.14, 2, and 2.71. All divided by 10 is 2.635. So for this next column, what we're going to do is take each observed value in the previous column and subtract 2.635. The last column, we're taking whatever value we got here and we're squaring it. So we're going to do these in one step. One thing that I like to do here to make this go a little bit faster is I take that sample mean, because I'm going to subtract the sample mean from every single one of these values, rather than have to type it in from scratch each time, I store it. So I'm going to take this 2.635, and I'm going to hit the store key along the bottom left, and then I'm going to hit the x, comma t, comma theta, comma n key, and hit enter. And now anytime I press this x, t, theta, n key, it's going to use 2.635. So I want 3.8 minus, I'm going to use x, right, minus, I stored x to represent 2.635. That gives me 1.165. And then I need to square it. So I'm just going to do that directly here by hitting the squared key so I don't have to retype. And I get 1.357225. I'm going to keep all these decimal places because we want to get a more exact answer by keeping decimal places and then rounding at the end. The next one is 1.55. So 1.55 minus 2.635 gives us negative 1.085, and then squared is 1.177225. 2.24 minus 2.635 is negative 0.395. Squared is 0.156025. 2.89 minus 2.635 is 0.255. Squared is 0.065025. 3 minus 2.635 is 0.365. And squared is 0.133225. 2.76 minus 2.635 is 0.125. Squared is 0.01565. 3.26 minus 2.635 is 0.625. Squared is 0.390625. 2.14 minus 2.635 is negative 0.495. Squared is 0.245025. And 2 minus 2.635 is negative 0.635. Squared is 0.403225. And then 2.71 minus 2.635 is 0.075. Squared is 0.005625. And so the reason I left this bottom row is we actually need the sum of all of those x minus x bar squared values. You'll notice that that sum is going to be the numerator over here in our sample standard deviation formula. So we need to add all those up. So we've got 1.357225 plus 1.177225 plus 0.156025 plus 0.065025 plus 0.133225 plus 0.015625 plus 0.390625 plus 0.245025 plus 0.403225 plus 0.005625. And you'll notice what you get for that sum is 3.94885. And so again, that is the sum of the x minus x bar squared values, which is the numerator here in the formula. So we have 3.94885. We divide by not just the sample size, but the sample size minus 1. So I had 10 GPAs there, so I'm going to divide by 9. So I'm going to take my 3.94885 and divide it by 9, which gives me 0.43876, but I still need to take the square root of that. So we did second square root of second answer and hit enter. And we get 0.6624 if we round to 4 decimal places as our sample standard deviation. Okay, so what that's telling us is that on average, each honors student's GPA deviates from the mean of 2.635 by 0.6624 points. Okay. What I also want to show you is how to do this much faster using the calculator. So for the other group, which was the honors students, we're going to look at how to use the calculator. So the first thing that we would do is hit stat and enter on edit. So stat edit, and then in list 1, we would enter each of the GPAs for the honors students. So 3.85, 4, and you'll notice I already did that, okay, 3.85, 4, so just all the way through to the last, the 10th one, which was that 4.0. So you'll enter those values in list 1, and then we're gonna hit stat again. And this time we're gonna scroll over to where it says calc, for calculate, and we want to do one variable statistics. So we're going to calculate some summary statistics for one variable. That variable is the honors GPAs. Okay, so we're going to hit enter on one of our stats, and then just continue to hit enter here because it says list 1. Frequency list, you want to leave blank. We don't have frequencies for each of those GPAs, and so just scroll on through, and it'll give you output that looks like this. Okay, you'll notice that we looked in the last section at finding sample means. I want to show you that that's how you would do this on the calculator. So it gives you the sample mean for this group. So remember, the sample mean for the non-honors group was 2.635. Looks like the sample mean for the honors group is 3.93, so we would expect it to be higher. That makes sense. The standard deviation, instead of using this whole process, we just look right here and we get 0.0594. And that's what we were asked to find. So 0.0594 when compared with, for the non-honors group, it was 0.6624. So as you can tell, there's a much more spread or variability in GPAs for the non-honors students than there is for those honors students. So just so we get a little practice writing what an interpretation would look like, we would say here, on average, the GPAs for the honors students are 0.0594 points away from the mean GPA of 3.93. So we're looking at the average distance from the mean, right? On average, the GPAs for the honors students are 0.0594 points away from the mean GPA of 3.93. So the other thing I wanted to make sure we're aware of is that the units for standard deviation match the units of the original variable. So because these were measured in points, right? GPA is measured in points, so is our standard deviation. If we were looking at a variable that was measuring, let's say, tree height in feet, then the average tree heights would be in feet, and the standard deviation of tree heights would also be in feet. So those units stay the same as the original.